This topic, Gauss's theorem, is very important in electrostatics. With the help of this one, we can calculate difficult electric field due to some object, some charged object. Uh, Somewhere we cannot use uh, Coulombic Coulombic laws to find the electric field directly, because there is a tedious calculations is present. Now, with the help of these Gauss's theorems, we can easily find the electric field due to some symmetrical object. So, Gauss's theorem says that the total flux through a closed surface. Suppose a positive charge is placed at the center of this spherical cell. This is imaginary cell. So, according to Gauss's, the total flux passing through this one is equal to total charge inside of this one divided by the epsilon naught. This is a very important theorem. Let us prove this. Suppose a positive charge is placed at the center of at this point, and since this is a positive charge, its electric field should be away from this one. So, taken a Gaussian surface. Suppose if I take symmetrical Gaussian surface, normally the spherical surface can be very good Gaussian surface. Any other surface is also possible, but this is very simple Gaussian surface, due to which we can calculate easily the electric field at somewhere. So, this is known as Gaussian surface. Gaussian surface. Now, it's suppose radius is r. Taken a small piece on the surface whose area is ds. Electric field at this point is away from this one, because at the center there is a positive charge. Electric field is away from this one, and taken a area, small area, it's a direction of the area vector is away from this one. So the small flux passing through this area will be d phi E is equal to E dot ds. Since E and away and ds is also away from the positive charges, angle between them is theta is equal to 0 degree. Now, using this one, using the scalar dot product E ds cos 0 degree, it comes out E ds. And we also know from the Coulombic law, electric field at a r distance will be 1 upon 4 pi epsilon naught q upon r square. So, electric field at the point of this, at the point of P, suppose E is equal to 1 upon 4 pi epsilon naught charge divided by r square. If I place this value at the point of P, I will get the flux passing through this one. Now, we need the total flux passing through this closed surface. This is known as the Gaussian surface. So, we need to add all the contribution of each piece of this surface. Because these pieces are small, these small pieces are continuous in numbers, so we cannot add directly. Numerically, we cannot add. We can just integrate this quantity, because integrations means only adding all these fluxes. So, the total flux becomes here. The electric flux now phi E. Just integrate this quantity. Now, putting the value of E. Now, this flux phi E becomes E. Put the value of E here, which is this 1 upon 4 pi epsilon naught. 1 upon 4 pi epsilon naught q divided by r square. There is a formula from the integration. Since x raised to the power dx cannot n plus 1 divided by n plus 1. So, this r goes in the numerator, and constant terms should be outside. R raised to minus 2 into ds. So now we have to integrate this quantity. Total electric flux comes out is phi e, and integrate this value e ds, and the value of e at a distance of r comes out 1 upon 4 pi epsilon naught charge upon r square. If I place here, the electric flux becomes 1 upon 4 pi epsilon naught charge upon r square into ds. So this is the total electric flux due to the whole surface. So we have adding the contribution of each small piece ds. So whatever the constants you taken outside, the whole thing is the constant. We don't integrate this. We have integration only the ds. So here, 1 upon 4 pi epsilon naught q upon r square integration of ds. We have to integrate ds. We have to integrate the small area ds. It means that we have to add all the surface area of the small piece on the surface of this spherical cell. So since we already know that if I calculate this one, this comes out the total surface area of this spherical cell, that is the 4 pi r square. So we have just put the value of integration of ds, which is 4 pi r square. So therefore 1 upon 4 pi epsilon naught q divided by r square into 4 pi r square. If I simplify this one, 4 pi r square cancel out, it comes out q upon epsilon naught. So this is the Gauss's theorem. Gauss's theorem says that the total charge inside of this Gaussian surface, is imaginary surface, and total charge which input inside of this in q divided by epsilon naught. Hence we proved this. Now applications of from Gauss's theorem. Here we have to find out the electric field due to a point charges q at a distance of r. Now from the Gauss's theorem, so suppose this is a positive charge, we need to calculate electric field due to this point charge at a distance of p. So using the Gauss's theorem, we know that Gauss's theorem, the electric flux, suppose phi the electric flux due to this Gaussian surface. Take a symmetrical Gaussian surface. Here the spherical is the very best suited for finding the electric field for using a Gaussian surface. Now we know that the electric flux due to this Gaussian surface, due to the electric field which is produced by the point charge, is equal to q upon epsilon naught. This is our equation number first. We have to utilize to find electric field at the point of this one. Now take a small surface area ds. ds is a small surface element ds. Now normally surface area taken its direction is outward drawn normal. So our outward drawn normal will be along this one. Electric field due to positive charge obviously away from this one. Now total flux passing through this small piece will be d phi e is equal to e dot ds. Since angle between e ds is 0 degree, therefore its value comes out e ds cos is 0 degree. Cos 0 degree has the value e ds. Now we need to calculate the total flux through this spherical cell. This is our the spherical cell. Spherical surface. It is a hollow one. Now total flux total electric flux becomes is equal, just indicate this quantity E ds. So E in magnitude everywhere is the same one. E electric field due to this point charges at a distance of r will be same. So we have just take outside this one any value which is a constant. You should have to take outside of this integration symbols. So only ds. Now if you add all these small pieces of area element, so I will get total surface area of this spherical surface. Now the spherical surface has a total value 4 pi r square. Therefore the integration ds comes out 4 pi r square. Now using equation number 1 in 2. Equation number 1 in 2 it says that total flux is equal to q upon epsilon naught. Therefore by the Gauss's theory q upon epsilon naught is equal to this quantity E times 4 pi r square. Now from here we can easily calculate the value of E is equal to 1 upon 4 pi epsilon naught q divided by r square. So from here we have easily calculated the field produced by this point charge q at a distance of r. So this is the applications of one of the applications of Gauss's theorem.